Okay, so I want to do a video to explain a bit about how to use the UFOLBM program. Um, so I've recently changed the input file for this so that it reads in directly from an STL file. So in the input file, what we've got here is the name of the STL file at the top, which I think can be up to 20 characters. So it's just reading this part here. Then you've got Tmax, and that is the maximum number of triangles in the STL file. So it just needs to be a big number because that's allocating the space for the STL file. And the form here is formatted, so that's saying ASCII or binary. So ASCII is 1, binary is 2 for the STL file. And the next one down here is the cell size. So this is the uniform cell size, which is dx, but it's dx equals dy equals dz. So what I usually start off with is we've got the STL file here, which is this motorbike case. And the first thing you need to figure out is the size of the domain that you want to use. I used to have a separate GUI for doing this for UFO CFD, but it's too complicated for this method. So what I tend to use, or what I suggest using now, is just to create a box source just for some visual guidance. So yeah, you just create a box source here, and then you can specify the size of the box, 822. So this gives you a rough idea of how your domain needs to look like relative to the object. So obviously the object has to be inside that. And this is the actual scale of the STL file. So it's, roughly, the motorbike's roughly a meter high. So, and then you can adjust the center of the box to get it aligned with the motorbike. So in the input file, what we need to specify is these values here: x min, x max, y min, y max, z min, z max. As that is just the size of the domain. So you do need to have a think about what size box you're going to use, the limits of the box. And then the other thing is, I'll put it here, is x live, y live, z live. So this is kind of like your live point, which is where the flood fill starts from. But it's also the point at which is used as a monitor. So when the program's running, it will export a velocity monitor from that point. But obviously, this point here needs to be within the domain. So here I've chosen 9, 1, and 0. So 9 needs to be within x limits, 1 needs to be within the y limits, and the 0 needs to be within the z limits. So it's quite compact, but that's all done there. So when you actually generate your mesh, lattice Boltzmann has to be a uniform mesh. And so this is the sort of thing you end up with. So it needs to be quite fine. So typically for a car or a motorbike, you might be looking at cell size of 1 centimeter, but it could be more or less. But as soon as you change the cell size, it affects the overall mesh size quite drastically. And then here I've got JSIM and KSIM. So this is putting symmetry boundaries on the J boundaries and the K boundaries. So the upper and lower is J and the front and back is K. So if you set those to 0, they'll be periodic boundaries. But if you set them to 1, both of those to 1, then they'll be symmetry boundaries. And the next one down is flow solve. So I put a flag on the flow solver because you might want to run the program but not do the flow solution. In other words, you might just want to generate the mesh. So that is so you can switch the flow solve off if you literally just want to generate a mesh and have a look, check that the mesh is in the right place. But I've got a slice through the mesh here, so if I switch off the other stuff and the mesh here, what it's showing is LCD is the useful one because that stands for live, cut cell, or dead. So that's LCD. So that's why it's called that. An LCD, live mesh is 1, the cut cells are 0, and then the dead is -1. So if the so when it's before the flow solver starts, it creates the uniform mesh, and then based on the live point, it does a flood fill, and so that generates all of the live points. And everywhere that isn't flood filled is by default dead, so for the lattice Boltzmann method, all of the cut cells in the dead region is the obstacle, which means that the flow isn't going to go there, or at least it's supposed to bounce off that region. And it's not essential that you have all the dead zones. I mean, it doesn't really matter if there's a leak, because it's still gonna the obstacle is still going to be defined by the cut cells, and so but I think it's just nice to know that if you've got a watertight geometry, then that you haven't got any leakage in there, but it should still run fine even if there is leakage into the inner regions. But I just decided to do it this way because that's the same method I used for the previous UFO CFD code, and it's quite pleasing when you post-process the results and then you can see it like this. And then because this is a slice of an actual solution, you can go down to the other ones, which is nu T, which is the eddy viscosity. You've got the density. I'm not convinced how realistic the density flow field is, but the velocity, it looks like that in this case. So obviously you want to switch that off. So the actual flow solution is literally just these three parameters: the eddy viscosity, the density, and the velocity. So if we just go back to the input file here, if you're going to run it for real, then you'd obviously want the flow solver set to on. Now these next three parameters might be a bit confusing. N-its is the number of iterations, but it's the number of iterations per save. So if I want to just run 10,000 iterations and just have one save of the VTK file at the end, then I just have n save to 1, and then it's going to do 10,000 iterations, then save at the end. But if I want to generate, say, 100 flow solutions during that, then I would have 100 saves, but then change this to 100. So that's going to do 100 iterations and then save, or rather it's going to do 100 repeats of this number of iterations. And quite often, if I'm doing a big demonstration case, I'll have 1,000 iterations for each step, and it will do that 100 times. So that's going to generate 100 VTK files. So the total number of iterations is actually n save times n its. And n out is just the output frequency. So it will just literally write a line out, a line of text every 10 iterations. So that doesn't really tell you that much. It just gives you an idea of how quickly the flow solution is going. So I normally leave that to 10, but you can change it to 1 or increase it to 100. Right, the full VTK has got 3 settings. So that can be 0, which is off, which means it won't write the full VTK solution. I can have it set to 1, which means it'll write the full flow solution just once at the end. Or I can set it to 2, which means it'll write the full VTK flow solution at every time it saves the data. So, but I tend to leave that to 1 because I just want the full solution writing once at the end. But if I change this value to 2, then it will effectively write the full solution 100 times. But you don't really want it to do that because otherwise it's generating too much data. Right, down to the slices. This again is a little bit complicated. If you want a slice of data, you can change these values. So the first one is for an I slice, the next J slice, and the next K slice. So you can have 3 separate slices. So I normally set those 2 to 0 and then have 1 K slice. So I might want a K slice halfway through the domain. But again, it's going to generate one of these slices 100 times according to this setting. So I could set them all off and then it won't do any slices, or I could have just K slice, or I could have J slices and K slices. But this is what I use to do the animations, because you don't want a full flow solution, you just want a slice of data. And literally what it's saving is just 1 slice. So just 1 slice like that. So that's for the slices. And the rest are the actual solver parameters. 1 here is for the regularized lattice Boltzmann method. So I would leave that at 1 now, because now that it's working for regularized lattice Boltzmann, which means high Reynolds numbers, there's not really any need to change that. But the original formulation is set to 0. Right, the next things are the solver parameters. There's only 4 things to set really. That's the Reynolds number, the length scale, the lattice velocity, and the Smagorinsky turbulence. So Smagorinsky value is supposed to be in the range 0.1 to 0.2. So this is just how much viscosity is put into the flow solution. So it affects the smoothing very much. But I found that even a value of 0.1 seems quite high, and so I reduced it to, you can even have 0.4. It depends on the case, but you might need something a little bit higher because the flow might start to look a little bit oscillatory in places if it's not high enough. So you can adjust that and see how it changes. Now this is lattice velocity. Now you shouldn't really need to change this much. You can leave it at 0.04. What is it? You don't want the flow solution to go above 0.33 anywhere. So 0.33 is the highest value of velocity that you want to have in your flow solution, otherwise it will become unstable. And I think that's why we use quite a low value for the lattice velocity, so that you prevent the highest value of the flow from ever being above 0.33. That's kind of like a stability limit. And the LREF is the reference length. So if you're doing a flow over a cylinder, for example, LREF is the diameter of the cylinder. But if you're doing a car, then which length scale do you use? You might use the height of the car, or you might want to use something less than that. Typically, it's kind of the size of the eddies that are being generated in the flow solution. So it's kind of open to interpretation, but the reference length has to be in lattice units. In other words, it has to be the number of cells. It's not a distance, it's the number of cells covering a distance. So for example, here I've used 30. So that means that I've set the reference length equal to 30. So 30 is kind of quite a small distance here, and that's because I wanted to capture more more eddies and have more resolution of the eddies. But if I was to draw a line on here, like a line source, now I can put 0.5, 10. Oops. So that is going up 1 meter. If I change that to 0.1, if I zoom in on that a bit, so that line is 0.1 meters long, but in lattice units it's 10. So in other words, if I want a reference length of 0.1 meters, then I'll have to put in 10 units for the LREF. And likewise in this case, I think I've got it set to 30. So that means 30 units. So in this case, the reference length that I'm using is 30 lattice units, which is about the radius of one wheel. I mean, that seemed about right for this case because it's kind of like the size of the crash helmet or that sort of thing. But I mean, that's another thing you can play around with. But essentially, that for lattice boltzmann, you literally just specify the Reynolds number, the reference length in lattice units, and the velocity. And so those are the parameters really. So once you've set the input file correctly and then run the case, then you'll get this sort of flow solution, and you can have a look at the flow solution and then see what it looks like. You can just, and when you load in the flow solution, you just have to select surface, and then you can choose one of these values here. So that is a brief introduction to how you set up this solver.